Everybody to episode 8 of Games with Go. We are learning programming by making a bunch of small games. So last time we got a basic prototype of Pong up and running, and today we're going to work on kind of refining it a bit. And as is often the case in programming in general, and games included, it's oftentimes very easy and fun to get something basic that works, kind of a proof of concept working, like we did yesterday. But you got to go through a bit of a grind to actually finish something completely and make it work well. So this is what we got working last time. It's just a very basic proof of concept. It's got a few issues. We're not keeping score. And we wrote down some of the things we wanted to do last time. And so we're going to address some of those today and get things working a little better. All right. So first thing I wanted to do is I made the choice last time to make some of these things ints and some floats. I'm going to make everything floats. Just to clean up the code a little bit, we kept having to do a lot of casts because of that choice that I don't want to have done. So really quickly, we're going to go through and adjust everything. So we don't need this anymore. I don't think we're going to need those anymore. So this also wanted to make floats. When we do that, we can get rid of a lot of this casting. So if you're familiar with C or C#, you might wonder what all this casting is for. Some languages do implicit casting. So if you set a float equal to an int or an int equal to a float, it will cast it for you according to internal rules of its own so that you don't have to. So the benefit of that is it saves you some typing and trouble. The downside is it's not always explicit what is happening. So like if you don't have C's rules for implicit casting memorized and on your mind all the time, you may not know exactly what is happening. Is the float being turned to an int? Is the int being turned to a float? Is the float rounded or truncated? And so on. Let's get all this stuff. You still have to have some casts, but not as many. Okay. I think we're done with that. Okay. Next step is probably the most important one, which is frame rate independence. So right now our game just does things as fast as it can and then delays for 16 milliseconds. And this will mean the frame rate will be about 60 frames per second unless your computer is very slow, because our game is very simple. So all of this stuff's going to happen approximately instantly inside of our game loop. But faster computers will play the game faster and slower computers will play it slower. And we don't want that. We want the game to happen at the same speed no matter how fast the computer is. So there's a couple ways we can do this. They all involve keeping track of how much time has passed. And Go has a library for that called the time time. So we can go ahead and add an import for time. And one of the first things we can do is we want to keep track of the current time, which will let us capture the elapsed time. So the time package has a let's do this. We're going to have a variable called frame start. which will keep track of what time it was when that's fine, when the frame first started. And you can get that by calling time.now. Okay, and time.now returns a time struct, which contains the time that happens when you call it. So then we'll know that. And then after all of our stuff has happened, all of our rendering and updating, we can compute the time at that point. Now you could say, new time is equal to time.now again and do subtraction, but there's a shortcut. We're going to make elapsed time variable 2. I think that's called time.duration. So you can call time.since, pass it a start time, and this returns a duration object or duration struct, and then you can get a representation of how much time has passed in different units. So you can do nanoseconds, seconds, and so on. So we're going to do seconds, and that returns a float 64. So we're going to make that a float 32 because we're going to try to always work with float 32s. Oh, so this should be a float 32. Okay. So elapsed time will now tell us how much time has passed from the start of the frame to the end of the frame. So one way you could try to make your game be consistent is just to lock the frame rate. So you could do something like, so if we wanted this represented in milliseconds, we could divide by 1,000. So this would be milliseconds now. So we could say something like delay for 16 milliseconds minus the elapsed time. Make that an int. Why is that not happy? Oh. Oh, this is a uint 32. So what this would do is just make sure that the game runs at 60 frames per second, no matter how fast or slow your computer is, unless your computer was so slow that more than 16 milliseconds pass, then this approach wouldn't work. This isn't really a good idea unless you know that all of your target machines can hit that frame rate. Sometimes consoles do it this way, like the first, what's the game? Dark Souls on PlayStation kind of did things that were just locked to a certain frame rate. On consoles, that can make sense because the machines are all the same. But we're not going to do it this way. We're going to be a little more clever. What we're going to do is anytime we update the state of our game, when we're sort of doing our physics-y type stuff, we're going to pass in the elapsed time. So let's actually leave this as seconds. So we'll pass in elapsed time like that. And what that will let us do is instead of moving our things by some fixed number, is we can scale it by how much time has passed in the frame. So if the frame happened really quickly, we move it less. If the frame took a long time to run, we can move it more. And I'm also going to make the paddles have a speed. So we can set that when we create the paddles. And same for the ball. Well, the ball's already got speed. It's got x velocity and y velocity. So let's do that now. So let's see here. This is going to be, all this stuff's going to get scaled by speed now. So, right, instead of just adjusting by the speed, we're going to say speed times elapsed time, and this needs to take in elapsed time float 32. Okay, this should remain the same. Okay, so we were just, when the ball went past the edge of the screen, we were just putting it at 300, 300. I wanted to make a little utility function for that. Position. So this will get the center of the screen. Return a position. So this will make a new position, which is when width divided by 2, comma, when height divided by 2. That needs to be a float. Okay. And then we can say equals get center. Does that work? Yeah. Okay, so then when the game starts, the ball will start in the very center, even if we adjust the screen size. So that'll be good. We also need to update the paddles. So paddles now will move by the paddle.speed times the elapsed time. Paddle.speed times elapsed time. And this needs to take in elapsed time. If anyone has any questions about what we're doing, feel free to chime in and just ask on chat. I'll check on it. So we're not going to use this yet, but we will when we make this better. Okay, so now paddles have a speed that we need to pass in. Where did we put that? Second to last. Let's see. So we're going to need to make it pretty big. Because the elapsed time is going to be pretty small. And we'll need to make this bigger too. Okay. Let's give it a run, see what it looks like. Okay. It's still working. Okay, but now what we need to do down here is get rid of this delay. What we could do is have no delay at all, but that actually won't work sometimes. So it seems okay here. But the problem you can have sometimes is if a game's really simple and running really fast, is that the elapsed time will be extremely small. Like we can actually print it out and see. Okay, so that's not too short right now, which probably means something in here is too slow. So we'll have to look at that. Yeah, we'll have to look at that in a little bit. But what can happen sometimes is you'll end up with these really, really fast frames, and the elapsed time is such a small number that your floating point calculations don't even work very well. So sometimes what you want to do is limit the frame rate to not be more than, say, 144 or 200 frames per second or something. So you can do that by just checking on the elapsed time and seeing if it's less than a certain value. So this would be less than 5 milliseconds, which would mean 200 frames per second. So we're going to limit it to 200 frames per second. And then So if we delayed for less than 0.5, then we will delay until we get to 5 milliseconds. And then we'll need to compute the elapsed time again. After the delay, so that our update functions get the right value. All right. So now we'll have a nice consistent frame rate no matter what computer we're on. I keep losing. Okay. So that gives us a basic frame rate independent setup. So we checked that off our list. Other big missing thing is we're not keeping score anywhere or drawing it. So we need to be able to draw the score to the screen. If you look at the original Pong, they had like a really simple number font. And so we're going to try to make something similar to that. One way you could do it is you could add a whole font rendering library to this and do it that way. But that's actually not very simple to do, especially since SDL is just a very low-level library. And even when you have the TTF font extension, you don't really want to just use that directly. You kind of need to render those fonts to textures and then reuse the textures. Otherwise, it ends up pretty slow. So let's make our own fonts from scratch, which will not be too hard because we're only going to support a few numbers. And they don't have to look very good if we're going to go for authentic Pong style. So here's one way you can do it. We're going to make a multi-dimensional array of bytes. And that just means we're going to have an array, and each element of the array is going to have another array inside of it. And we're going to have just a 3 by 5 array of numbers. Yeah. All right, so you might be able to see where I'm going with this. This is going to be the number 0. And then we're going to do 0, 1, 2, and 3. Just so we don't spend all day on stream typing in numbers. So this needs to be 1, which we can do like this. So you can actually just literally draw it in your code. You could also move stuff like this out to a external file if you wanted to. So that's going to be a 2. This will be our 3. Does that look right? Looks good. We'll check it when we're done. All right, is that all happy? Var nums equal. All right. Go formatter doesn't want me to do what I want to do. All right. Fine. All right. So we have some very primitive numbers there. Now we need to draw them. So let's do a draw number function. So we'll take a position to draw the number at, take a color. size. So we're going to make it so we can scale the numbers to any size we want. Very advanced. The number to draw and the pixel buffer to draw them into. All right, so let's get a start x. It's going to equal to, so again, we're going to use the position to represent the center of the number. So we're going to get the height and width of the number. Size times 3 because it's 3 elements wide. Size times 5 for the height divided by 2 because it's 5 elements tall. And to draw these numbers, we're just going to take each byte in this array and draw a square. And the square size will be determined by the size input here. So for index and value in our number, right, so this index num will take us to either 0, 1, 2, or 3. And then we're going to iterate over that inner array one at a time and look at the value. So if the value is 1, then we're going to draw our square. So we're going to go from start y to the size of the square, y plus plus, start x plus size, and then we'll just set our pixels to x, y, color, pixels. And then after we have drawn, let's see. Okay, so after we've drawn each square, we need to advance our start x over to the next square. And once we've drawn 3 squares, we need to go to the next line. So we need to go down by 1 square. So move y down 1 square and then put x back at the start. So we'll subtract size times 3. Funk. It's unhappy here. Set pixel. Set pixel. Okay, so let's just test it out real quick. In our game loop, let's draw number, put it in the center. Make it white. Let's make it pretty big. And we'll do the number 2. Pass out our pixels buffer. All right, our number 2 is goofy. Probably just have extra 1 in there. Yeah. So let's close. All right, we got a 2. Okay. So now we want to actually draw these numbers as part of the score. So we can make the score just part of the paddle. And that will be an integer for sure. And when our paddles start out, they will have a score of 0. And then in our update for the ball, we can tell when to change the score on a paddle. So we're going to change this around because currently we're just resetting the ball when it goes off the screen. What we need to do is set the score for the appropriate player and then put the ball back in the middle of the screen. So if the ball goes off the screen to the left, then the left paddle has missed it. So the right paddle score needs to go up. And we'll put the ball's position at the center. And else if ball.x has gone greater than the window width, then the right paddle has missed it, so the left paddle's score increments. Then when we draw our paddles, we can also go ahead and draw the current score that they have. So one thing I want to do, let's save that, is I want to draw the numbers kind of up above, like they did in the original Pong. Not quite right above the paddle, but kind of towards the center of the screen. And to help with that, I'm going to make a quick function called lerp. And lerp is something that comes up in game programming all the time. It just stands for linear interpolation. And basically what it's doing is if you have, say, some values, so you've got 1 and 10, and you want to put something in between your two values, you want to put it like, say, halfway in between, then lerp will give you the number halfway in between. Or if you want to get 20% in between, it'll get you the number, 20% in between, and so on. So let's give that a try. So lerp functions will always take in two values. We're going to do floats. That's the interval that you want to interpolate between. And a percentage, which is how far in between them you want to go from A to B. And it's pretty simple math. Take your starting point, A, plus the percent of the distance between the percent times the distance between B and A. Right? So that's it. That's lerp. And this is really useful. It's used all the time. I think this is even built into like shading languages for 3D cards. So that's how useful it is. All right, so now when we draw our paddles, we want to draw the numbers in a good place. So let's get a starting position for our numbers to be drawn, and we're going to use lerp. We're going to take the paddle position x value. We could just say x directly, can't we? So that's our starting point. And then we're going to get the center of the screen's x value. And then we just want to go a little bit towards the center of the screen. Okay, so it'll take the left paddle's number will move a little towards the center, and the right paddle's number move a little towards the center. Why are we not happy? Oh, declared and not used. Not yet. Then we want to draw our number. I'm going to do it at position at our starting x, and then y value just a little bit down. Is the paddle's color. Try size 10, because 20 was a little too big. And the score is the number we want to draw, and the pixels buffer. Okay, so let's give it a go. All right, we've got our score. It's 0. It goes up to 2, to 3, and then it crashed. And it's crashing because our score got past 3, and we don't have a 4. So it tried to index the array where it didn't exist anymore. So we're going to have to check for that. All right. So let's go ahead and do that. Okay, so yeah, let's talk about game states. So it's common for games to have a lot of different states they can be in. You can be playing the game can be paused, you can reach a game over state or a or a state where it's time to go to a new level. You need some way to keep track of that. A common way in smaller games is to use an enum. Go has a sort of bizarre syntax for enums that I don't like very much, but it is what it is. So we will use it and deal with it. You can make constants. There's this crazy keyword iota. So together, this whole bit from here to here becomes like an enum in other languages like C# or Java that you might be used to. Basically, all this means is you need some way to keep track of whether the game's in progress, whether you're starting, whether you're pausing or whatever. So you can give names to your states, and these are just represented by integers. This is going to be 0, this is going to be 1. You could go on 2, 3, 4. But rather than having to say something like, if the game state is 1, and then remembering that 1 means something, you're giving the 1 a name. And this const keyword means that these values can't change. You can't change the value of 1. Start is always 1. So it's a handy way to make your code easier to understand because you're going to use descriptive words for the state instead of numbers or some other identifier. And it's better performing than it would be to use, if you could use a string, but strings are kind of expensive to compare. Okay, so we're going to start just with a game start state and a playing state. If you wanted to flesh this out more, you could have like a game over state that displays a message or so on. And you could have a pause state if you wanted to have a pause menu. We're just going to keep it at 2 today, keep it simple. And then down here in our game loop, we're going to do different things depending on whether the game is in the game start state or in the play state. So if we're playing, we're going to do pretty much all the things we've been doing. Let's move this clear down just before we start drawing. That makes more sense. And then, yeah, so if the state of the game is in the play state, did I name this state? Oh, I need to make a state, I think. Let me do this. Okay. So we'll do it right under here. State equals start. So we're going to start out at like the start screen. All right, so state equals play. We're going to do all the stuff we've been doing, all of our updating. Let's take out our test number. Let's if state equals start. This will be like our start screen. We're going to wait for the player. We'll say the player needs to hit spacebar to actually get going. So we'll check our key state. Remember, the key state array has the state of all the keys on the keyboard, whether they're pressed or not. And we're going to look for scan code space. And if that is not equal to 0, it has been pressed. Then we'll set the state equal to play. We're also going to check the player score. If yeah, so this is where we'll reset the player score to 0. This should be equals. Okay, so as soon as I press state, we press space, we reset the score, set the state equal to play. So we'll go back to playing the game. And then I think over in our balls update function, where we're checking to see if the ball has left the screen, Right, this is where the ball's left the screen. We're going to say yeah. Okay, let's do it like this. So we'll say state equals start. So anytime the ball leaves the screen, the ball is going to start, go back to the middle, and wait for spacebar. Right, so everyone's got a moment to get settled when you play the next point. And then we only reset the score if one of the players has won. So player 1 scores 3, or player 2 scoring 3. Then we'll reset the score. Right, let's give this a try. Okay. Okay, I need to lose. All right, good. So now everything's pause, start over, pause, start over, back to 0, 0. Okay. So now we have something a little more playable where we're keeping score. Now there are still some bugs in here. They're not immediately obvious. One of them is it is possible for the ball to get stuck sometimes. And also the ball is, you can see it's actually going past the paddle a little bit, like it's going halfway into the paddle. And that is because we're not adjusting for the ball's radius when we hit the paddles. So let's do that real quick. So we want to check to see if the outside of the ball is touching the paddle, not the middle. So we'll subtract the ball's radius from the left paddle and add it to the right paddle. Let's see what that looks like. All right, now you can see the ball's bouncing as soon as the edge touches instead of the middle. So that's good. So the bug that can happen here, maybe not because our frame rate is so fast now, but it could happen. Oh, you saw it there. The ball did something bizarre. So what can happen in games when you're doing collision detection? Let's erase. So all we're doing is when the paddle, or rectangle, touches the ball, right? Our ball has some x velocity. Maybe it's -5 because it's moving to the left. When it touches, we're just making that +5. So on the next frame, the ball will be over here instead of back here. But because our physics is not running at infinity frames per second, sometimes what will happen is on one frame, the first time the ball is touching the paddle, the ball is actually inside a little bit. And then so on the next frame, when you've gone +5, the ball might still not quite be off the paddle. And so our logic currently would make that -5 again, right? We would go minus. And so the ball can end up kind of like, ball can kind of end up like getting inside and then kind of wiggling around. And you see like bizarre stuff happen like this in physics in many games. Like if you've played Battlegrounds lately and seen things shoot off into the sky, it can be because of issues like this. So there's a concept called the minimum translation vector, I think it is, which is just figuring out once you have a collision event between two things, what's the minimum amount you need to move this ball back this way so that it's not touching anymore, right? So we'll have the collision resolved and not wiggle back and forth. So in this case, that's not too hard to do. We can just set the ball's x value equal to the outer extent of the paddle plus the ball's radius. Then here we do the right paddle dot x minus the right paddle's width over 2 minus the ball dot radius. What are we unhappy about? Oh, ball dot x. And so that will make sure that anytime the ball collides, that it actually leaves the paddle and starts going the other way. So it should prevent those weird cases. So collision detection is hard. Even in this really simple 2D game with rectangles and circles, it's hard. It gets harder if you have polygons, even harder if you go 3D. But you always have this issue with collisions. All right, what other little things can we look at? Let's see. Oh, joystick. So I have an Xbox controller, but you can do this with whatever joystick you have, if you have one. So this game's kind of nice to use with an analog stick. It can let you move the paddle slower or faster. So I'm going to do that. If you don't have an analog stick, but you have like a gamepad, it's not too hard to adjust it to work for that instead. So to use joysticks in SDL, you need to open them. And to open them, you need to see how many there are. So we'll start with, we're going to make an array or slice of controller handlers. So that will be pointers to game controllers. And then we're going to loop over how many game controllers there are. So we'll start at I equals 0. I is less than sdl.num joysticks. So that will tell you how many joysticks are plugged into the computer right now. And so we're going to append to our controller handler slice each game controller we open. So we can call game controller open, and we give it the index. So 0th controller, first controller, and so on. And this gives us this will add like a little struct that gives us the functions and properties of each game controller, filling up this slice with them. And then you're supposed to close these, and the defer function comes in handy here. You can say defer controller handlers I dot close. Okay, so this will currently run kind of before our game loop starts. If you wanted to handle the case of letting someone plug in a controller while they're playing and detecting it and picking it up, then you need to make this logic a little more complex and bring it into your game loop. You can absolutely do that, and it's definitely a good idea to do so. Okay, so now as well as checking for our events, and you can check for joystick events in here, and it works fine if you're looking for button presses, but for the analog stick movement, it doesn't work very well. That's kind of happening all the time, returning different values as you move it. So it's better just to check that on its own. So we're going to loop over every controller in the controller handlers slice. We don't need the index, so I'm skipping it. So if controller is not equal to nil, it's just a safety check. Then we want to get, in my case, I want to get the controller axis value. And we're going to declare that up here. That is an int 16. So I'm going to say controller axis equals, so you take your controller and you can call get axis. So if you have any kind of analog sticks or joystick and so on, you can call get axis and you tell it which one you want. So if you start typing this out, you'll see there's axis left X, axis left Y, right X, right Y. You kind of have to experiment or read the documentation to see how these map to various controllers. It's usually pretty sane though. So for my Xbox controller, if I do left Y, I get this controller, this stick right there. And this number will be a value between negative 32,000 and positive 32,000. That's the range of int16, potentially, if it's calibrated right. And we're going to use that to move our paddles as well. So in order to do that, we will need to pass our paddle update function, that value, so that they know about it. Paddle update. So we'll do controller axis int16. Okay, so currently in update, we're just checking for the up arrow and the down arrow. So now we're going to add a check for the controller axis. And one thing you want to do with controllers is the zero. Oh, Control C Ninja asks, does defer work properly in loops? Yes, it does. The order might not be what you anticipate. I believe that defer goes in like the opposite order that you say them in. But yeah, you can use defer in loops. Like the loop index value gets copied, I believe, so it works like you would expect. Right, so controllers are not always perfect, and so you can't count on the axis value being 0 when the user is not touching it. So you want to give a little bit of room that you're going to ignore, like small values you're going to ignore and pretend they're 0. Otherwise, the controller is kind of like drift around. So first, we're going to see if the controller axis is actually big enough to even worry about. We have to convert to float 64 because the built-in ABS function. This is absolute value. So if it's negative, it'll turn it positive. If it's positive, it leaves it alone. We're going to see if that's greater than, say, 1500. And if it is, then we'll go ahead and get we want to compute like what percentage the controller is moved, from 0 to 100%. And so we'll make this a float, and we'll divide by the maximum value it could be, like that. And then we'll say paddle.y plus equal paddle.speed times the percent times the elapse time. Okay, so this is the paddle's maximum speed. So if the user is pressing the controller all the way up, this will be about 100%, so they'll get the full speed. If they're pushing it halfway, it'll be about 50%, so they'll get half speed. And then times elapse time to scale it for how fast our frame rates are going. So I'm plugged in. Let's give that a try. Space to start. And there we go. And I can move it. You can see I can move it slow or fast. All right, and you can get at all of your, joysticks and controllers functions. You can kind of explore the controller object to see what's in there. And you can also use SDL to like make the rumble things rumble and so on, and do force feedback. All of that stuff's available. Okay. So we got joysticks. We got game over state, win lose. We got scores. We got frame rate independence. So there's still more things we could do. We could handle letting the user resize the window. and that involves sort of scaling all the drawing you're doing based on how the window is drawn. We can make the AI more realistic. Right now it's invincible. And we could also allow for two-player versus single-player. So we're not going to do all that tonight, but this is stuff you guys can do on your own to practice. Be a good idea. Oh, one other thing we need to do is like, so there's a couple ways to do this. The way that the original Pong made the game work is if you hit the ball on the more towards the edge of your paddle, it would make the ball deflect at a different angle. So you could on purpose hit the ball like on the very edge to make a sharper angle to try and defeat your opponent. You could do some other things like maybe if you hit the ball while you're moving, maybe the paddle could impart some vertical velocity to the ball, like some percentage of the paddle's velocity, which again would let you, uh, try to trick out your opponent. So those are some good things to play with, because right now the ball always just bounces perfectly off your paddle, which isn't super interesting. And I think the original Pong also made the ball continually get faster and faster and faster. So that's something you could try too. Any questions about the stuff we've done here tonight so far? Okay, so next episode, which will be should be Sunday, 8 p.m. We're going to do some procedural generation. It's going to be noise functions in particular, like simplex noise and perlin noise, which are used in tons of games. Like if you've played Minecraft, the terrain is created by noise functions. If you've played Elite Dangerous, or pretty much any game that has millions of possible planets, those planets' textures are created often with perlin noise or simplex noise. So we're going to do some really cool stuff with that. It's going to be really cool graphics. It will not be black and white. We will have all kinds of colors. And it's going to be fun. And then we'll do another episode after that where we make the noise get generated in parallel. So we'll use all of our cores on our CPUs. So that's what's coming up. And if you want, you guys can refine the Pong game and make some crazy Pong games. Everything's kind of set up so you can change things pretty easily. Like you can start giving things color. You can make the length of the paddles change, make the speed of the ball speed up and slow down. So have fun with it. All right, I will see everyone in a couple days. Good night.